Okay guys, so good morning. So first of all, thank you to everyone for coming along today. I know it's quite short notice, but it's really nice to see the good turnout here. First of all, thank you to the City of Cape Town Coastal Management Office. Is that how they? Yep. For housing us here. So Mandy is from SPAW. She's just going to give us a quick health and safety and familiarization with the location spiel. So over to you, Mandy.
Hi there. Okay, just to let you know, toilets are behind you, the back. Okay. Kitchen, very clearly marked if you need anything. That is a fire escape exit and also exit there. Those are the only two exits actually in the building. Okay. If you do need anything else, I'm just around the corner in the office. You can just come and knock on the door, and hopefully I can actually help you out with whatever you actually need. There is going to be load shedding at 2 o'clock, but we do have an inverter, so we can actually use the extension cord, and Circle here will be able to actually help you out when load shedding happens. Okay.
Well, thank you very much. And also just to say, have fun. This is a working office over on the other side, so just be respectful of that, obviously. And thank you so much to Mandy and to Greg and the Shark Spotters for allowing us to use the space today. So thank you. Part of the African Bioacoustics Community Conference. Our ethos is really to make scientific knowledge, and particularly on the field of bioacoustics, available to as many people as possible. So within that ethos, we are going to be recording as much as possible today so that it goes up onto the YouTube channel, so that then other people who haven't been able to attend today, haven't got the finance to come from Canada, we had somebody, but also from other places in Ghana, Muizenberg, so on, so that they can also benefit from the expertise of Jakob and Ole. So we also have, so we also have other experts joining us online, so I'm hoping that the load shedding isn't going to mess with that too much. So we've got Catherine Carr, who is based where across Jakob?
University of Maryland.
Okay, and then I do believe we also have another...
Adam Smith coming from he's at the SDU now, but he'll join us too.
Okay, so those guys are going to join in online. And then I'm going to leave it to Ole and to Jakob to introduce themselves.
I'm Jakob, Christiansen-Dalsgaard from the University of Southern Denmark. I have really looked forward to being here. I thank you for coming on such short notice too. And a lot of the hassle for poor tests and so on has been our slowness in our poor organization from SDU. But thanks anyway, and thank you very much for helping. I would also say that the reason why we are here is that there was this funding of the two-piece workshop where we had the first one in Kruger last fall, and we should then have one here, and we have decided that this one should be more on perception, sound perception and hearing. And also because the focus in the earlier one was very much marine mammals. This will be very much terrestrial. So you that are marine people, you'll have to hang on. I would also say our group in Denmark is specialized in bioacoustics. So we are 5 permanent staff, 2 emeriti. Ole is one of them. He will introduce himself in a moment. And we work with all aspects of hearing and sound communication almost. So from whales to frogs and lizards, and we don't really cover insects very well at the moment, but that might change. Birds and of course bats, echolocation, all these kinds of problems. And we had tried out of all this to pick out a day for you. And I know that it will be very kaleidoscopic, but I hope that you will take the chance during these breaks to ask us questions whenever there's anything you would want to hear more about, because we really had to sift through our work and pick out stuff. So, but thanks for coming, Ole.
Well, like Jakob, I've spent most of my working life in Odense, Denmark. Denmark is a small one on top of Germany. And I've worked on all aspects of sound communication in animals, starting out actually on insects. I worked for many years on orthopteran insects, grasshoppers, crickets, and so on. I've not been into bats though, but I've been into birds and mammals and marine mammals. I worked on walruses actually for a while. But some 5.5 years ago I became emeritus, and I've been able to work together with Jakob a little bit, but of course it's different to be emeritus than to be an active researcher. What else do I need to say? Well, also I worked on bird migration and navigation for a while, and one of my students is now a world expert in that, so that makes sense. What else? Just looking forward to the interaction with you. Please ask lots and lots of questions, because I just, took some old lectures and then, fitted it a little bit, hoping that you would ask lots of questions.
So I thought I would start very, very briefly with saying a little bit about what sound is. And this, for those of you that were there in Skukusa in the fall, it will be very much a repetition. For those of you that were there, it will be very, very brief and superficial. But bear with me on that. So definition of sound. What is sound? What kind of a thing is it? Well, we know that it's a wave that propagates in an elastic medium, but very, very fundamentally important, and something that I think we don't realize, is that sound is always generated by motion. So you always, whenever you have a moving object, you generate sound. If I do this, I actually generate sound. My hand is just a very poor sound emitter at 1 Hertz, but there would be sound and you would be able to measure the sound emitted. If you're in water, it's much easier to generate sound. And that's actually something that people, that is a problem when people, for example, report sounds from underwater turtles or things like that. They put a microphone down and they record a variety of sounds, and then they say, oh, there's a huge repertoire of this underwater turtle, but some of it is just the turtle bumping into each other, turtles bumping into each other, turtles scratching, turtles farting, turtles. So it's actually something you have to realize whenever you do sound recordings, that any motion, sound is motion, and motion is sound, so to speak. And that is also kept in the sound wave, because it's this oscillation between a pressure when the particles are moving together, and the motion of the sound particles. And all sound sensors, wherever they are ears or microphones, they would be sound sensitive. They would be motion sensitive. They really respond to motion. A microphone responds to the motion of the membrane. An ear sensory cell responds to the motion of the sensory hairs. Here's a little animation of what a sound wave would be like, and see that it starts by something moving here, right? It's always a motion that translates into the sound wave, and the motion is kept because you will have movements of these particles. Some definitions that are useful is that we can talk about the frequency of sound, the number of wave cycles per second. We can talk about an angular frequency that's often used in bioacoustics, where you just multiply the frequency by 2 pi. We can talk about the wavelength, which is the distance between 2 wave maxima, and the wave number. And that's actually an important number, which I will return to. That's the reciprocal of the wavelength. And then you can talk about the phase, which has something to do with timing of the wave, when it's zero crossing is hitting, when it's happening. But very fundamentally important here is the number Ka, and I'll return to that later. But that's actually the size of an animal defined by its radius multiplied by the wave number. And that number sort of defines how the animal interacts with sound. You could call it its acoustic size. It depends. It defines how good it is at receiving sound. It defines how good it is at producing sound to a large extent. But so bear in mind the number Ke. There's a wave equation that defines the relationship between frequency, wavelength, and sound velocity. And that equation is simply that the sound velocity is equal to the frequency times the wavelength. And that's a very useful equation. That makes it possible for you for any given frequency to calculate the wavelength, which again has something to do with defining the acoustical size of the animal you work with. C is the speed of sound, and that in air would be around 340 meters per second, depending on temperature. And in water, it will be around 4 times higher, 1500 meters per second. And it's also dependent on temperature, but also very much on salinity and other factors. So if you know that sound velocity for any frequency, you can calculate the wavelength. So the wavelength for a 1 kilohertz tone would be 34 centimeters in air, and in water it would be 1.5 meter. So in order to define the relationship between the motion component and the pressure, there's this simple relationship which reminds you maybe of Ohm's law for electricity. So it says that the pressure is equal to an impedance times the velocity here. So if you know the pressure, you can calculate the velocity, the speed, the velocity the particles are moving with, because the impedance is characteristic for the medium. And it depends on the density, and it depends on the sound speed, so it's much higher in water than it is in air, reflecting that air is a lighter medium than water. Let's also just touch the dB scale, it is a logarithmic measure of sound pressure, and it's a relative measure because you take the sound pressure related to a reference 20, which in air is 20 micropascal, and in water is 1 micropascal. For some irritating reason, it would make it much easier if they were the same. But the water people wanted to be different, and that should be allowed of them. So once you know the sound pressure, you can calculate the dB SPL, and this is actually developed originally as an intensity measure. And if you do intensities are the square of the pressure. So then you use these formulas. If you use energies or intensities, you use this formula here. And the normal audiograms we see, thresholds are plots of the thresholds usually for terrestrial animals in dB SPL. And here you see, for example, one for a gecko, a tokai gecko, or an audiogram for that. You can calculate easily with dBs, but there are two nice units, numbers to remember, and that is that a doubling of something that equals 6 dB, and a 10 times increase equals 20 dB. And conversely, if you halve something, it's -6, and if you decimate something, it's -20. And if you have these two in mind, you can almost calculate any dB values in your head. So, a fundamental thing about the sound wave is that the energy is spread out as the sound wave propagates. It radiates in a sphere, and the sound pressure will be smeared out over a sphere, but you have a constant energy coming from the sound emitter. So that means that the intensity will drop with the square of the distance, and you have this formula here. And because intensity is pressure squared, then it means that the pressure will drop with the distance. So there's a linear drop of pressure with distance. which, or not linear, sorry, inverse, inverse with distance. So that means that if you double the distance, you decrease the sound pressure by 6 dB, as a rough estimate. And Ole will probably tell you that there are a lot of environmental factors that can mess this up. But our rough rule of thumb is that sound decreases by 6 dB for each doubling of the distance. Okay, so these were just sort of the ground rules for acoustics. Now let's talk a bit about hearing. We're communication people, right? So we always focus on sound communication as the argument for why animals hear. But that's just a little part of it. And actually that's not what creates the most sensitive hearing. When we're talking at a comfortable level, we're talking at 60 dB SPL. We're talking 60,000 times above our thresholds. No, the guys that really need to have a good hearing, that's guys like these that listen for predators, or predators that listen for weak rustling sounds of animals that have no intent of communicating with them. These are the best hearers. These are the ones that are selected for and has the best survival. By the way, about nothing is known about hearing of impalas or many other African mammals. Almost all African mammals. Very, very little is known about what they actually hear. Rhinos, anything. So what is the function of hearing? Yeah, well, generally, hearing alerts you to any mechanical disturbance. This is again the motion thing. So hearing alerts you to something that moves in your environment. Sound and vibration are an indicator of that something is happening. Whereas your visual system doesn't readily give you the same information. But whenever you hear sound, you know that something is happening. You walk in the forest, you hear a knack of a branch, and you know that either there's something moving or there's a branch about to fall down, maybe on my head. So you should react to this. And it shows a change of the environment, and it's something that happens that you can use even when in darkness and so on. So hearing is a fundamentally important sense for that. And for the simplest kind of things in hearing, and I will spare you for an experiment I usually do with my PhD students in our school, where I make them close their eyes and sit and meditate for some time and then explode something next to them. Because this shows you the first of the four functions of hearing, which is the acoustic reflex. So if you hear an intense sound, the first thing that happens is that you will be very, very quiet. And in fact, every physiological thing in your body will quiet down. Your heartbeat will stop for a moment. You will have a hormonal response, which makes you, which sort of tenses you to find out what is happening. So that's what's called the acoustic reflex. It's found in almost all animals. But of course, in order to do something with the sound, you need some more processing, and that's the expensive part of the processing. That's the acoustic imaging, the identification of where and who the sound source is, and to separate sound sources from each other, which is not a mean task in a flock of penguins with 200,000 penguins, where each parent has to find their chick by their calls, right? And they're all calling at the same time. So the tasks, the computational task of untangling all these sounds that are reaching the two eardrums is formidable. Then we have communication. That's in a way is what we always think about when we think about hearing. But as my claim is that this is a very derived thing on a system that already is functioning, and communication is fairly is in a way easy, because it is usually at fairly high sound levels and so on. And then we have the echolocation, which is a derived form, you could say, of communication, which is what your whales and bats are using to find their prey, emitting sounds, high frequency sounds, and listening for the reflections, and doing a very complicated processing and imaging based on these sounds. So this is the function of hearing, and the function of the types of ears that we see I'm afraid that's Catherine that's lost from Ole. Can you see if there's any message from her? I think you have to move over there. Oh, sorry. Ears are, as I said, ears are mechanosensors. All ears are mechanosensors, so they respond to some mechanical deflection. And in this case, I've shown you different types of ears. From the simplest one, and this looks like a vertebrate hair cell or something like that, with a sensory hair bundle up here, and when you bend it, you get an excitation of the, you get a depolarization of the cell and nerve responses. I'm not covering insects at all here. We can talk about it. Ole is really the insect expert, so you should assume you should talk about it. No pun intended. But insect ears are generally working more or less the same way. They would have a sensory hair that would deflect and that would create a response. But then in our animals, we generally we see in many of the terrestrial animals that this that this mechanoreceptor is coupled to a mechanical apparatus. So that would be a tympanic ear, and the function of such a tympanic ear is simply to increase the vibrations, increase the mechanical stimulation of this cell, right? So the better the tympanic ear is, the more bending you will get of these sensory hairs. There are two main types, and I probably won't go very much into that for time reasons, but you can either have an enclosed tympanic ear like we find in the mammals, or you can have a connected tympanic ears where the two eardrums can communicate, and that gives these animals that have that, and that's more or less all tympanate animals except mammals, that gives them some extra chance of having a directional ear, because you have some interaction between the two sides. Let's look at some ears, and let's start in the water, even though I will not go very much into water, but from an evolutionary point of view, that's of course where we all came from, so it might be instructive to look at that. So fish living in water have roughly the same density as water, so we would say that they are more or less transparent to underwater sound. Little sound are reflected from them. Their Ka is generally much less than 1, so the frequencies they hear correspond to very long wavelength, and the ratio of their size to that wavelength is very small. And that means that the sound will simply push them back and forth. It would be like if you're on a big boat and it's carried up and down by the waves. So you're just moved by the sound. And the fish ear is excellently suited to work on this movement because it has a stone, an otolith, lying on the sensory cells, the hair cells here. And when you accelerate the fish, because its otolith is dense, its movement will lag a little bit behind the movement of the fish, the rest of the fish, including the sensory cells. So they will be bent by the movement. And the ear would respond to acceleration. And fish ears are generally all working that way. So you see the big, there are usually 3 ear stones, otoliths on each side, that are angled in different angles. So that also means if you are responding to particle motion, which is the translation of the body, then you can easily calculate what the fish will receive at any given pressure. So if this is a toadfish, and as you may know, they make a toadfish boat whistle. So they say that lying on the bottom of the sea. And so a very long 200 Hertz tone at a fairly high intensity of 2 pascals underwater. And if we calculate what's coming out of that, it should be a 2 here, but the number is right. Then you get a displacement velocity of 1.4 micrometer per second. And that corresponds to that the fish is moving one with an amplitude of 1 nanometer or so. And that's actually interesting because we can relate that to the auditory thresholds. They're about 1/10 of that 1 nanometer. So what this means is that the fish should actually only be able to respond to things that were 10 meters away if we apply the distance law. Yes?
Some of the terms you're using in terms of auditory thresholds, perhaps you could just elaborate on those.
Yeah, I mean, the auditory threshold is what you measure from the auditory nerve. People have measured this in toadfish. So they have vibrated them and then they have had a microelectrode in their auditory nerve. And then they have just measured how much you needed to stimulate them in order to see a response. There are different ways to measure a threshold, but that's the usual thing is that you just inspect it. So when you can see, or rather when you can hear something, you say that that's the threshold. What's that? Is that clear? Okay. And so this is sort of surprising. There's a story to it though, and that is that the fish has another way to amplify these motion cues. But the basic thing of it is that if your ear is working just by particle motion, it's really unusable for long distance communication. You really want something else. And the fish has some fish have actually done something with that, because if you couple your vibration measurement, vibration sensitivity, if you couple your ear to an airfield structure, which in fish typically is a swim bladder, then that will actually increase the particle motion, because they will move much more than the rest of the water does, and you will get a much more sensitive ear. And there's a whole group of fish called the ostariophysites, which is normal fish like carps and goldfish and zebrafish and so on. They are ostariophysites. They have a special apparatus, little bones here that connects the swim bladder vibrations to the inner ear. And actually, to finish the toadfish. The toadfish has some outpocketings of the swim bladder that goes up and gets quite close to the ear. So it also gets an amplification of particle motion. So that's a situation in water, and that's a situation for most of the ancestral fish of ours. They didn't have these kind of connections as far as we know. They were lungfish, and they had an otolithic ear. So what's the difference once you are a fish on land, so to speak? Well, the speed of sound is 4 times lower. That means that the wavelength for the same frequency will be 4 times smaller. That means that your Ka for the same frequency will be 4 times larger. And your impedance will be 4,000 times smaller. And that means that the particle motion cues will be larger at the same sound pressure. So at the outset of it, the fish is actually vibrated quite a bit by a sound. So if we now take our toadfish and put it on land and stimulate it in air, this number is still not correct. Sorry, this should be true, but this is right. If we stimulate it in air and measure the displacement, you will see that it's actually using a model that we had grasped from an acoustician called Morse. That the movement of it is actually 9 times higher in air, which is sort of counterintuitive. But you should realize that making 2 pascals in water and in water and in air is not the same thing. It costs much more energy to make 2 pascals in air. But for the same sound pressures, the fish will actually get a large motion. So the toadfish, according to this model, which doesn't take in the effects of friction and so on, there will actually be a quite large movement of the fish at low frequencies, depending on the Ka. If the Ka of the fish is very much smaller than 1. So small animal at low frequencies. So this is sort of the standard. This is the way that it started, and the way it started for the tetrapods going on land was the first ones of them look a bit like this. And it's a bit of a cheat to say that they're actually going on land, because animals like this were probably living completely aquatic. The first tetrapods were living the life of their ancestors, their relatives among the crossopterygians, and probably not really going on land. They were using their hands as paddles and so on. And it can be shown that these animals had a non-functional tympanic ear, so they had an inner ear like everybody else, but they didn't have anything that looked like a tympanic ear. And they must have been hearing more or less in this way here, we guess. And in fact, the tympanic ear originated much later than the first tetrapods. So if we have the origin of tetrapods here around the Devonian, around 370 to 400 million years ago, that's down here. You can see that these orange blobs are where we guess that the tympanum, the real air-adapted ear, originated differently in the different groups, probably independently in the neurons, certainly in the mammals. And how the relationship accurately is here, we don't really know. It may have been originated just once, but the current consensus is that the crocodiles and the birds, the archosaurs, the lizards, and the turtles independently developed a tympanic ear, which is a device for making efficient hearing in air. So here you see the tympanic ears of the four of the recent groups. You have the frog, the lizard, the bird, and the mammal. And it's easy to say why in the old days people thought that this represented sort of a line of evolution, right? That's because they are so similar. It was difficult to explain how the mammals should have shot two extra middle ear bones into a functioning ear. And that was difficult to get around. But what the consensus now is that all these are independent experiments in hearing, right? They have all used a similar bone, which was non-functional in the early tetrapods. It was a structural element, but developed the tympanic ears independently. And that, of course, that's an evolutionary novelty that has changed their hearing. It increased the sensitivity of the ear, it increased the directionality of the ear, and it increased its frequency response, so they would be able to respond at higher frequencies. And especially the mammals, as we will see, got some special functions out of having the extra ossicles. And what happens here is that the large tympanum collects sound energy and makes a much larger movement of the middle ear bone that you would otherwise have. So it's all about making as big a splash as possible in the inner ear fluids. And that is what is done by the tympanal system here. And I think that ends this part of the presentation. So, questions? Yes?
Considering they're sitting in shark spotters, I was wondering whether or not, because they're cartilaginous, how the otolith or how the hearing system works.
Oh, that's a difficult question. Sharks have a special feature in the ear. I mean, they basically have the same ear as fishes, but they have a large portion of sensory cells called the macula neglecta. And people have speculated very much about what that macula neglecta is doing. And there are also some studies that showed, some old studies that showed that people were playing underwater sounds from sharks, and they could attract them from 300 meters or so. But you should be skeptical of these studies, because what happens if you play sounds from an underwater loudspeaker, apart from playing sounds? You have movement, but you have one other thing when it's a loudspeaker. We have electricity, right? So you set up an electric field, and as we know,
yes.
As we know, sharks are really sensitive to electric fields, so I think some of these studies should be taken with some doubt. It would be very difficult to understand why that a shark should be able to hear in very, very long distances. They're basically stuck with the particle motion. Yeah, they don't really have any precious compressible element except the liver, which has a little bit lower density. But I don't think anybody has speculated that they use the liver. So it's a difficult question, but there's certainly something to work on, and it would be interesting to sometime to redo these behavioral experiments, but you need some control for the electrical field. Yeah. Cool. I just need to change